I want to talk about moment of inertia. Which is about the kinetic energy stored inside a spinning object. And the moment of inertia has some similarity to the mass. It's not the mass, it has a different unit, but it's in some sense like the mass of an object when the object is going straight. Moment of inertia is for rotating objects. Mass is for going straight. And since we're talking about spinning object, I have to first talk about the angular velocity and speed. So if you have something that's rotating, and let's say r is the radius of the circle. So imagine a particle rotating on a circle of radius r. Then let's think about the central angle theta and this arc length s. Do you know the relationship between the arc length s and angle theta and radius r? So if I give you the radius of a circle and a central angle theta, do you know the formula for finding the arc length? Does anyone know? No? You call this the SOAR formula. We'll just write SOAR. Because your theta looks like O, right? And simply remember it like SOAR.
That's applied in the length of the arc.
That's the formula for the length of the arc. And we are assuming that theta is in radians. This formula doesn't work if theta is in degrees. Okay, so this is in radians. Now, what's the rate of change of the distance? If you differentiate both sides, with respect to t, what's the rate of change of the distance? What is that called? Huh?
Position.
What's the rate of, huh?
Velocity.
Velocity. Actually, it's speed, because it's the rate of change of the distance. Rate of change of the position is called velocity, right? That's a vector, whereas rate of change of speed is, rate of change of distance traveled is speed, which is a scalar. But I still want to use v for the speed, and the reason for this is in your textbook in physics, if you write something in bold, that means it's a vector, but if you write something in a regular font, that means it's the scalar value of the vector, or the norm of that vector. So the standard notation for speed is not s, but it's v, written in regular face. If you write boldface, that's the actual velocity. But if you write like without the boldface in regular font, that's the norm of the velocity, which is the speed. So this is the speed, if you differentiate the distance traveled. And if it's going in a circle, the radius is a constant, right? That means I can bring the r outside, and you have d dt of theta. And let's think about what's the meaning of d dt of theta. That's how fast what's changing? How fast?
That's how it's changing of the angle.
It's the rate of change of the angle, right? Yeah. It's rate of change of how fast the angle changes with respect to time. That's what this is, right? And you have a name for that. That's called the angular velocity. And the standard, or angular speed, the letter that's used for angular speed is omega. So this one is angular speed. How many of you have seen this formula in physics? If you haven't, that means you're not really paying attention in class, okay? You should pay attention in all classes, okay? And they're all related, right? So this is saying the regular speed that we know of is radius times the angular speed. That's the first thing I want to use. Next thing I want to point out is, suppose you have a ring and the ring is really thin. So it's a very thin ring of radius r and mass m. The question is, what is the kinetic energy stored in this ring if its angular velocity is omega? Okay. So let me ask this question. What is the kinetic energy if this is rotating at angular speed omega? Solution, and it's quite simple. Kinetic energy formula is what? K equals to
1/2 mv squared.
mv squared.
But it's a circle, so it's changed.
But, the mass is given as capital M, so we're going to use capital M. And velocity, we know, is r omega, right? And by the way, this radius in this picture will be capital R, right? So we have r times omega as your velocity squared, and that's going to be 1/2 m times r squared times omega squared. Now here, this is simple to answer because if this is a thin ring, every point here is going at the same speed v. Do you agree? Right? Because everything is radius r away from the center. So you can just use this, so that's the answer. However, if you ask the second question for a disk, things can get really complicated. So let's talk about that. Same question, but this time it's a disk. Disk of radius r, and again, the mass of this object is m, capital M. It's rotating. Now this time, you immediately see that things in here would be what? Slower or faster than the ones near the center? Which one is faster? The one where it's outward. As you go outward, it's faster, right?
It's taking up more time.
If you have the same angular speed, if they're rotating the same way, right? After 1 second, which covered more distance?
Outside, because
the outside covered more distance. So of course, the outside will be faster. Well, but what's really important is that you can no longer make the same argument like how we did here because things are moving at different speeds. In other words, things outward here would have more kinetic energy stored than the things inside because the outside is rotating at faster speed. You see the problem now? Okay. So asking the same question, what k is, now becomes a lot more challenging than before. That's where this concept of moment of inertia comes in. So moment of inertia looks at this formula and say, okay, when things are rotating together, velocity is no longer a good thing to use. When rotating together, everyone has the same angular velocity, but different linear velocity. So we give up using v, but come up with using this idea of using omega. Okay? And then instead of using the mass by itself, we think about mr squared as what's called the moment of inertia, and we write like 1/2 I omega squared. So the new formula for kinetic energy will be like 1/2 I omega squared, where I is equal to mr squared, and this is called the moment of inertia. Which, by the way, has no relationship with momentum, but historically people started calling this for some reason, and then the word just got stuck. So it's an unfortunate choice of words, but its actual meaning is something that acts like mass when you have a rotating object. So that the formula you write is very similar to this one. You can see that I corresponds to m and omega corresponds to v. Right? So if you replace the velocity by angular velocity, then the distance unit of length squared has to be attached to the mass, and that quantity is called moment of inertia. Okay, so let's ask two questions in this case. When you have a disk, a solid disk rotating at the same time, I want to find out the kinetic energy and also the moment of inertia for this case. Okay, how do you do this? First, anything is?
1/2 mv squared.
No. We're trying to use integration.
So it's going to be integral dk.
dk, right? Universal formula, okay? And we have to figure out what I mean by dk. And the choice of dk is like this. We already figured out that on the same ring, they have the same velocity. So it's easy to figure out the kinetic energy if you divide this into concentric rings. So you divide this into very, very thin rings, like that, a lot of them, and then find the kinetic energy for each one of them, and then add them up. It will give you the total kinetic energy. Okay, we also need a few other things. I'm going to put this on the coordinate system so it's easier for us to see what's going on. And we're going to put the circle, put the disk so that the center is at the origin. And we're going to parametrize these rings by using x. If I do that, what is the thickness of this ring? Thickness is this, right? What is that? dx. So here's our picture. In one strip, this is x, and this length right here is dx. Moreover, I also need to talk about the mass of this small ring, but we learned that when it comes to talking about a small portion of the mass, it's good to use the surface density, right? So what is surface density again? Mu is mass divided by area. And we're going to assume that this object has constant density. In other words, it's a uniform object. So that anytime you want the mass of some portion of it, you just multiply the area by this mu. That's how you get it. Okay. So I think we have pretty much everything to figure out the decay here. So that this is, imagine that this is rotating with angular velocity omega. And we already found out that k is equal to this formula here. 1/2 mr squared omega squared. But you have to be careful. Instead of m, we have the mass of this portion. So what should I write? It's not the mass of the entire thing. Yes?
dx.
dm. dm. Right. It's the mass of this small chunk. Okay. Which, if you add them up, you'll create the entire mass. Okay. And also in this picture, instead of the radius, which one is replacing r? X, right? It's this. This is radius, right? It's x, right? So this will be x squared omega squared. But then we also have to figure out what dm is. And as I said, you convert the area into mass by multiplying by mu, right? So we need to say mu times dA. And now we have to figure out what the area of this small thin strip is. And here's my argument. If you cut this circle strip into half right here and you open it, what shape would you get?
You would get just a straight strip, right?
You'll get a rectangle, right? Whose thickness is
dx.
Yes.
dx, and whose length is?
L. Or
But what is that? What's this L?
I want to say diameter.
What's this length?
Circumference.
Circumference, that's the word, okay? What's the formula for circumference?
1/2.
No, that's area. Yeah,
Is equal to 2 pi r.
2 pi r, right?
Wow.
Circumference formula is 2 pi r. But as I said before, the radius is x, so this length would be 2 pi x. So this is what you get. You get mu times this, so it's 2 pi x times dx. Oh, sorry, I should have said dk. Okay. So the kinetic energy of this small portion, dk, is same as this, with dm being replaced by this, and therefore we have the following calculation. Which is integral of 1/2 x squared omega squared dm, which is mu times 2 pi x times dx. Where x goes from 0 until r, right? This, if you have concentric circles, the smallest circle has radius 0, and it increases until it reaches r. Right? So adding up all this, calculating this will give you the kinetic energy. Let's identify the constants. So 1/2 and 2 cancels. Omega, we're assuming that it's rotating at a constant speed, so omega squared is constant, mu is constant, pi is constant. So we have omega squared mu times pi, integral from 0 to r of x times x squared, which is x cubed, dx. Now you integrate x cubed, you get 1/4 x to the 4th, and you're plugging in r and 0, which gives you 1/4 mu times pi times omega squared times 1/4. Oh, I already pulled the 1/4 out. R to the 4th. But this is not satisfactory because we invented our mu while solving this. So we have to figure out what mu is. Mu is mass divided by the area, but what is the area of this circle? What's the area of the circle?
R squared.
Pi r squared. We plug that in here. Let's see what happens then. It's 1/4 times m over pi r squared times pi omega squared r to the fourth. R to the fourth divided by r squared will give you r squared. You have a m. You still have 1/4. And pi cancels, and you just get omega squared. Okay, that looks a lot simpler. So that's our answer for the kinetic energy. Now here's a question. What is the moment of inertia in this case? Remember, moment of inertia is like, this should equal to 1/2 I omega squared, right? So for these two to be equal, I should be what?
1/2 mr.
Yeah, 1/2 mr squared. So for a rotating disk, the formula is 1/2 mr squared. Just look at your physics textbook. You'll see that 1/2 mr squared is there for the disk, and for a ring, there's the mr squared. Let's do just one more example, or maybe two more. See, the problem is, although physics 1 assumes that you've done calculus, it doesn't really use integral calculus that much. So the physics textbook might have this in there, but it doesn't really try to use the integration that much. But if you start doing these calculations, then you gain more confidence into what you're doing, and you actually can do these calculations having the feeling that you're actually understanding what's going on. So this should be really valuable in your physics class. All right, let's say you have a rod that's very thin, and the length is L, and its mass is, again, capital M. And let's assume that it's rotating around the endpoint. So you're rotating like this. If that's what's happening, what is the kinetic energy and inertia? That's the problem. Okay, so kinetic energy, once again, kinetic energy, what's the inertia? And you still use the same idea, but before we do that, it's always that the question of density comes up. If you have a thin object, then you need linear density. Okay? Because it doesn't have area, it doesn't have volume. Those values are close to 0. That's what you need. Okay? So linear density is defined as what? What over what?
Linear density is
M over
length.
length. So that if you have any small portion, then you multiply the length by linear density, you will get the mass of that thing. Now what you're going to do is, now you're going to say k is equal to integral of dk, just like before, the universal formula that always works. And we have to figure out how to chop this. But one-dimensional objects, there's only one way to chop it, right? Like this. Okay. And we're going to put this on the plane like this. So what is this? That's, if you have a very small thickness in that direction, what's that? Dx. Okay. So we're going to parametrize this rod by two things. It's a very small thing, and it's like this. Here's, from here to there, that's x, and there's a small portion of the object that's dx, and this is rotating like that. Okay. Now let's figure out the mass. We're still thinking about k equals to 1/2 mv squared. But v is equal to r omega. We have to use this formula where r is now, in this picture, if you're rotating like that, what's the r? X is replacing r, right? So v is really x times omega. That's what we have. That goes into v. And this mass is the mass of this small thing, right? So this mass is really dm. This is mass of this small thing. And mass is calculated by lambda times what?
lambda times, like,
length. And the length of this object is
x.
dx. Very small object, right? Dx. So that's going to replace this formula. So that's going to be your dk. So dk, the kinetic energy of this small portion of the entire rotating object, dk would be 1/2 times lambda times dx times x times omega squared. And x would go from 0 until L, right? So that's what we have to do. Integrate from 0 to L of all of these added together, 1/2 lambda x squared omega squared dx. X squared omega squared. Then we pull out all the constants outside. So 1/2 lambda omega squared, and you integrate from 0 to L of x squared dx. And that's an easy integral to do, 1/3 x cubed. Plug in L and 0, and then you have to multiply 1/2 lambda omega squared. And this time it's even easier. We're almost there. So you have 1/2 lambda is m over L times omega squared. So this is lambda, 1/2 lambda omega squared. And then when L goes in here, it's 1/3 L cubed. 1/3 times 1/2 will be 1/6. L cubed divided by L will be L squared. You still have m, you still have omega squared. Okay, so now we figured out that this can be written as 1/2 1/3 ml squared omega squared. Therefore, what is I? Be this part, right? 1/3 ml squared. Okay. So that's the formula for a rod spinning at one end point. That's the formula for moment of inertia. And you get the kinetic energy by doing 1/2 I omega squared. Now, if you know how it rotates around one endpoint, then you can also figure out the moment of inertia when it's spinning at the middle, right at the middle. Because it's simply this. If you want this kinetic energy stored at the entire rotating object, you just divide it into 2, so that this object would have length over 2, and this will also be length over 2. Mass will be divided as m over 2, and this one will be also m over 2. Right? So think about the kinetic energy stored here. The formula for kinetic energy is this, except that you're only taking the kinetic energy of this part with smaller L and smaller length and mass. So you replace m by m over 2, L by L over 2, and then omega squared. That's one part of the kinetic energy, just by using this formula for that half. But then there's 2 of these, right? So you have 2 of these. And the end result is that you're going to get 1 over 2, 1 over 12 ml squared omega squared, if you simplify the algebra. If you factor the ml squared omega squared with 1/2 out, you're going to get 1 over 12. So that's the moment of inertia formula when you have a thin rod rotating around the center. And you can use this formula for even the case like when it's like, say, 3/4 of L here, and then 1/4 of L here, and then this is spinning. You can do it. Just find the kinetic energy here, and then you add them up, and you can find the moment of inertia using it that way. Okay. So that's the idea.